Okay, I'm good to go. Hi, everyone. My name's Edmund Jackson, as you heard. I'm here to talk to you about core.logic today. So I'm an independent consultant from Cambridge, as you can see. I used to call myself a statistician for about 10 years, and that was really great for getting to stand around alone at parties. But now I've started calling myself a data scientist, and I don't have that problem anymore, so that's great, because I'm so busy I don't get to go to parties. So slowly, okay. Sorry, I get nervous and speak very quickly. I'll slow down. So I was making a joke at my own expense. Right, so anyway, enough of that. Let's talk about core.logic. So, in the beginning were the ancient geeks. These were the guys who wrote the first programming languages and built the first computers. Now this was before the epoch, right? So there was no computer science. So they had to come from other fields, and they brought with them abstractions and built these wonderful programming languages with the one failure, which they couldn't actually run on the computers of the time. So they all sort of put aside, and we built an abstraction of programming language, which was of a computing machine, which is a machine which computes. And that allowed us to move ahead and to actually start to write useful stuff. But now 60 years down the line, we have the opposite problem, in that, this is not news. We've got these great computers. Like, personally, we have almost infinite computing power, but we're still sort of stuck in the old ways of thinking about programming. And what's been inspiring and uplifting about Clojure is that Rich and the guys behind it have gone back to these ancient wisdoms and are making them relevant by putting them on the JVM and plugging them into modernity. I mean, Lisp itself is the original word of power, right? God created the world with Lisp. This is known widely, right? And I'm here to talk about another, not quite so ancient wisdom called logic programming. Now, when I had a look about the talks that were out there and the various tutorials and the books, I was trying to find something that was actually, worth your time to actually listen to me. And I thought what I'll try and talk about is what you can do with it and why you might want to use it rather than how it works and sort of particulars about it. So that's what I'm going to talk about. You shouldn't smile, because really I'm just up here greasing the lip of one hell of a rabbit hole. Okay, so I can't assume you guys know anything about it, so there's going to be a hold your wigs quick tour of logic programming. So it'll be a bit quick, but it won't be too bad. So, hello world in functional programming. If I cons, I have a pointy thing. If I cons A onto an empty seekable, I get a list containing A. Yeah? If I cons B onto a list containing A, I get BA. I'm here among the warm embrace of the parenthirati. I need not linger there for very long. And the abstraction here is, this is a functional programming abstraction. I take a function, I apply it to some arguments, and it returns a result. Happy days, right? Everyone's clear with this, right? Relational programming just puts a little sign in there. And the semantic difference is simply that I make an assertion. So a relation or a goal in core.logic is an assertion. Think about it that way, it'll become clear. So I'm asserting that there exists a relation between these arguments, and that relation is named by f. So much like f specifies a function, f0 or f null specifies the relationship. So I'm saying between these arguments exists a relationship of some sort denoted by f. And that goal or relation can either succeed or fail depending on whether the actual values passed in as those arguments satisfy that relationship or not, right? So far, that's all there is, right? Now you can connect this up, and you can say, well, if I make my relation based on this function, I can say there exists a relationship between the arguments passed to the original function and the result that it came back with, and that relationship is f, right? So you're just bringing the result inside the argument list and asserting that there is a relationship between these things. So let's make this concrete. Here's my cons example. Cons A, onto the empty list, I get a list containing A. Excuse my vectors, it just makes it tidier, right? I'm calling them lists, we're all happy, right? So in logic programming, I'm just making the assertion that if I cons A onto the empty list, I get the list containing A. These values satisfy this relationship, this relation. Therefore, the goal as a whole succeeds, right? Again, if I cons B onto the list containing A, I get BA. That succeeds. If I cons C onto the list containing A, I get BA. Oh, wait a second. That's not the case. These values don't satisfy this relationship, therefore that goal fails. Again, cons C onto the list containing A, get the empty list? Not so much, right? So, in a nutshell, a goal succeeds if the relation it implies holds, if the values passed in and bound to the symbols satisfy that relation. End of story. Now you can start to raise things up a bit. Here are some other relations you could think of. I assert that the rest of the list ABC is BC, that the first element of the list ABC is A. This one we're going to use a lot throughout the presentation, that A is a member of the list AB, and that ABC is a permutation of the list BCA, right? But you can really easily see how this builds DSLs. I assert that Socrates was a teacher of Plato. This is true. And you can see how you can abstract things right out very easily by using this sort of a language. Right. So far so dull, right? This is like submitting work to a teacher, and you say, you know, I assert that 1 + 1 is 2, and he says, yeah, that's correct, or that's not correct. What you want is you want some degrees of freedom. You want some latitude, some wiggle room. So what you need are to pass symbols in which are not yet bound. So rather than passing values, pass symbols. Those symbols are called logic variables, and they look like symbols that you've seen before, right? So this Q is just a variable to which is bound a value. You know, now assorted malefactors and various ne'er-do-wells put this little sigil at the front. You'll see that in sort of Cascalog and Datalog type stuff. I won't do that, but if you see this sort of in the wider community, that generally denotes a logic variable as opposed to a normal variable. So here we go. This says, when I cons the value bound to Q into the empty list, I get the list containing A. So what can Q be? Clearly it can only be the keyword A, right? We can ask the computer to do that. This is the first complete logic program. It's read as follows. Return for me all, hence the star, all the values of Q such that when Q is cons into the empty list, I get the list containing A. And it will come back in some ways yet to be specified and say that will only happen if Q is the keyword A, right? So this is like a relational, like the SQL statement, right? You know, here's my engine. This is a binding for the variable that is the subject of the actual query. There can only be one in core.logic, so it's a bit redundant, but there it is. And this is the actual logical statement that you're trying to satisfy. What happens behind the scenes is core.logic goes through and finds all the values of Q which satisfy this particular statement. That's it, right? This Q can go anywhere. I mean, it's over there. It has to be A, right? Here, find me all the values of Q such that when I cons A into Q, I get the list containing A. Clearly, Q must be the empty list, right? The list containing A. But it gets more flexible, right? You can put this Q anywhere. It can be inside. And, you know, this logic engine's smart. And it's going to say, well, okay, find me all the values of Q such that when I cons A into the empty list, I get the list containing Q. And so, yeah, that's going to work if Q is the keyword A. So you can destructure, jiggle, and poke, and it's all just going to work out like a miracle, right? Now, there's some strange values as a result of the power that you get. How about this one? Return me all the values of Q such that Q is a member of the list ABC. This can succeed if Q is A, or if it's B, or if it's C. So this statement returns the vector ABC. This does not mean that Q is the vector ABC. What it means is that Q can assume any of the values from that vector and satisfy this logical condition. That's a man trap that, you know, I spent a lot of time playing around in. It gets worse. Not going to be multiple values, it can be all possibilities. Find me all the values of Q such that B is a member of the list ABC. Well, Q doesn't participate in that logical statement. So Q could be any value, that's denoted by the underscore, any value, and this is still satisfied. Or there could be no possibilities. Find me all the values of Q such that A is a member of the list BC. Well, Q doesn't participate, therefore it can't make this true, so it's never true. This statement fails. There's no way that Q can make this work, so therefore nothing that is bound to Q can make this logical statement succeed. Right, so how about this one? Which ancient geek is this? Well, clearly it's Uncle John, right? He's the founding genius of our field to which we owe everything. Right, so composition. We've spoken about the basic elements, the atoms that are involved here. We've got logic variables, we've got goals, and we've got a query engine. So after discussing atoms, you want to discuss composition. So how do we bring these things together to say more interesting stuff? So the first thing is logical conjunction, which is just logical and. If I take more than one goal and I place them in sort of parallel, or as a series, whatever, like this, they are joined in conjunction, meaning, let me read it for you, find me all the values of Q such that Q is a member of the list ABC and Q is a member of the list BCD. So to satisfy the first one, it could be A, B, or C, but in order to concurrently satisfy the second one, it can't be C because that's not, it can only be B or C because those are the values that are shared between the two. So when I put two in parallel like this, they're joined in logical and. Right? Just so we don't get lazy, remember you can put Q anywhere, and it's still going to destructure the whole thing out and work for you. Logical disjunction. So instead of and, or, right, that's the next logical step. That's denoted by this conde. This is here for historical reasons from scheme and Lisp conde, right? So if you put the logical goals inside a conde, they're joined as an OR statement. Sorry, an OR statement. Yeah. So this says, find me all the values of Q such that Q is a member of the list BC or A is a member of the list BQ, right? So in order to satisfy the first one, B or C are returned. And in order to satisfy the second one, well, it has to be A in order for that to work. So it returns all of them. Contrast that with the previous one, where it could only be A. And you see the difference between, and OR. Okay, equality. Actually, that's unification. So that's the first real step down the rabbit hole. After this talk, if you want to learn more, go read about unification. Everything is based on that. But I'm going to, in the nature of this talk, lie, cheat, dissemble, and elide. I mean, I told you I was a statistician, right? So you're expecting that. So I'm going to call this equality, right? So this says, find me all the values of Q for which Q is equal to B, right? B, end of story. Disequality is the opposite. Find me all the values of Q such that Q is a member of the list BC, but Q is not B. So it's got to be C, right? So now we've got is and is not. Finally, we want to increase the degrees of freedom that we have. Because we've only got one logical variable, so that's only one degree of freedom to express logical statements. So you want to have more locals, more vars, whatever you want to call them, and you introduce that with fresh. This introduces a logical context, defined by these parentheses, in which there's a new logic variable, E. And you can include it in your logic statements as you would the resulting query, but it's not returned itself. So this says, find me all the values of Q, such that Q is a member of the list BE, and E is A. So if E is A, that's the list BA, therefore Q can be BA, right? So E itself doesn't get returned because it's not the subject of the query. Right, who's this enlightenment geek? This bewigged gentleman, I'm not saying. Now, the most logical place to talk about this is in relation to data. Now, we've spoken a lot about data in this course, not course, listen to me, so far in the seminar. All right, so from the sublime to the pays the rent for everybody in the room, right? Select star from geeks where geek ID is 0, goes to the database, and it returns you some record, right? So in the OOP abstraction, you have your query object, which gets sent to your database object, and it sends your return object, right? In functional programming, you say, well, there's one arrow too many there, so there exists a function. You apply a function to the query and the data, and it returns you a result. So this is a bag of data. You actually bind it in. You know what it is. Logic programming says, well, there's still one red arrow too many. You can see I'm abstracting. The arrows are going away, right? That's obvious. And you assert that there exists a relationship between a query and a data. If you make this query something like a template, you can get some idea of how this works. So what is this mystical F? We've been talking about it. It's member O. So if D is my database, I'm saying, for which values of Q is Q a member of the database? If Q is some kind of template which matches against the elements of the database, you can see how that's going to work very quickly. So here's pseudocode. This is not real code, and it's not how you want to organize your data. People will talk later about far smarter ways of doing it, but it's pseudocode, right? Find me all the values of Q for which Q is a member of the database, and Q is a record with geek ID 0 and geek name I don't know. So that's equivalent to the SQL statement I put up earlier. So this will go through my bag of data, my database D, matching up my Qs, which are a member of that data and are also in that map, will look like that map. So far, so obvious. So, you have your big bag of data, you put it through a funnel, which matches some relation, and you get particular instances from it. Sorry, I bored myself there for a moment. Fortunately, logic programming can do far more exciting things, and we can load this funnel from the other side, right? And this is why people get excited about this. The original query looks like this. Find me all the values of Q such that Q is an element of D. I have this bag of data. Here's this bag of data. Find me all the elements Q that look like something, right? Turn it on its head. Run the statement backwards and say, well, I don't have a bag of data, but I have a template. Go find me the bag of data. Find me all possible values that look like this. I mean, that's unbelievable. My favorite talk from last year's conge was the logical statement was an interpreter, a scheme interpreter, and they said, well, this is a logical statement. Find me all programs that evaluate to 6. And off it went and did that. And I'll give you a link to that later. It's amazing. Just absolutely staggering. So that's a bit of an introduction to core.logic. I hope no one's bleeding from the eyes. You, stop bleeding from the eyes. And I thought, given that I'm trying to actually be a bit pragmatic here, I'll run through an example. And the problem is that on the internet there are two sorts of logic programming examples. There's, toy problem gentlemen with wolves and goats and cabbages, or there's, like death by fire type inferencing systems, and there's like this chasm between the two of them. And being the kind of guy I am, I applied my brain and thought, well, I'll just step into that chasm and produce an example. So we're going to talk a bit about timetabling for my ancient geek university. Is that at all obvious to people? You can see this? Bigger. I can't make it bigger without it coming off. Can I have more contrast on my projector? Anybody? No, you want it bigger? Okay, I was trying to avoid this while doing this live because I've managed to unbind my make text bigger key by using Sam Aaron. It's his fault. I'm using his, whatchamacallit. So I'm just going to make it bigger. But I can't do it because I've unbound the key, so I have to go into my Emacs config. And you know what happens when that happens? It all goes pear-shaped. Config. All right, you want bigger, huh? You got bigger. Wow, wasn't that an amazing use of fast shortcuts and the power of Emacs? Amazing. All right. Yeah, is that any better? That's as big as it gets, people. Okay, so let's continue. Okay, so here I'm defining some courses. So I'm trying to define a timetable for my ancient geek university. Now, I know what a timetable looks like. It's my answer. But I don't know everything about it. I can say things like I have certain lecturers who have to lecture. I have courses that need to be in there. And there's some relationship between them, right? So let's start with the basics. I have my courses. Let's just connect to my REPL, right? Load my namespace. Okay. So this is just a closure vector. It's courses with some keywords in it. Straight up closure, right? Then I can define my lecturers that I have. I've got Plato, Aristotle, Archimedes, and Herodotus of Larissa. He's a smart guy. He said, because we experience the world through our perceptions, what we don't perceive does not exist. And he died with his eyes closed in a bear pit. Yes, awesome. So the venues in which my lectures can be held are the Parthenon, the Senate, and prison. Right? And the students taking these lectures are the incanters, the rhetors, and the sophists. Right? And now we get back to the core tenet of closure, which is everything it's about the data. The data is the abstraction. Let's think about the data. The answer that I want is a timetable, right? So let's define what my timetable looks like. To make my life easier, I've made my timetable a vector. It's a vector of periods. So you can see, can you see my cursor at least? If I move it, can you see it? No? Oh, you can, cool. Okay, so the timetable format is a vector of vectors. Each of those vectors is a period. And the period has 4 elements: the course, the lecture, the venue, and the students, which are derived from here. Yeah? So let us build a timetable. So that's my answer. So I say, okay, core.logic, go and find me one timetable, right? So instead of Q, which was using earlier for my logic variable, I've called it timetable because that's more semantically meaningful. I need some degrees of freedom. So what I've got here, I've got the course in period 1, the lecture in period 1, the venue of period 1, and the students in period 1. And the same for period 2, period 3, and period 4, right? And then I finally said, well, to make this problem a little bit harder, let's have some courses happening concurrently. So I'm going to say that, periods 1 and 2, those two happen at the same time as those two, periods 3 and 4. So in order to do that, I had to put some structure on the answer. So I'm saying, okay, my timetable is a vector of vectors, where each inner vector is a period, as I described earlier, of a course, a lecture, a venue, and some students. So that's period 1, period 2, period 3, period 4. See, I've taken those logic variables that I defined earlier, and I've structured them up. And then I said, okay, the concurrent periods are period 1 and 2, and period 3 and 4, right? So far, so easy. So I said, okay, see what happens when you get big text? That's nasty. Find me a timetable, and you'll see the answer pops out here. So you can see this is a vector. It's a vector of 4 vectors, 1, 2, 3, 4. And inside are these sort of mystical symbols. The underscores you'll remember from earlier, it says it can be anything. So all I've said is I've got a vector of 4 elements, each of 4 elements. And it says, well, okay, those values can be anything you want them to be. I don't know anything more, so it gives you 0, it gives you underscores. So let's bind some stuff in. Let's say, okay, let's make sure that the courses that I've got on my list are actually taught. So here I'm asserting that the vector C1, C2, C3, C4, that's the vector of courses taught in periods 1, 2, 3, and 4, is a permutation of the courses vector that I defined earlier, this guy here. Yeah? This one. So I'm making that assertion. I'm saying that when you look at those values, they've got to be a permutation of courses. So let's run that and see. And it says, okay, yeah, sure. Here's my course in period 1, rhetoric, dialectics, mathematics, astronomy. And it says, yeah, that satisfies the logical condition that I put on it. Now, I can get greedy and I can say, well, I don't like that one. Give me 10 timetables, right? So instead of run star, I've got run 10. So don't give me all, give me the first 10. And not particularly readable, but believe me, it's got multiple answers there. But that's not very exciting. Let's find out how this works. So now we're gonna dig in a little bit. It gets ugly. So what does permo look like? Permo succeeds if V1 is a permutation of V2. And this looks a lot like sort of classical functional programming. I've got recursion, so here's permo, and it's recursing with permo, and I've got a base case and a recursive case. Definitely is just some sugar, baby, and all it is, that's all it is. All it is saying, give me a function where each of the elements of the body is joined in disjunction, so it's in a conde, right? So what I'm saying is, for every time you go through this, succeed if either this succeeds or this succeeds, right? We'll talk about the second one. So let's say, okay, here's some destructuring. I'm destructuring the first vector, pulling off the head, there's the tail, and here's a second vector. So in order for the first to be a permutation of the second, the head element of the first vector must be a member of the second one, right? That's clear enough to say. And then the sort of jiggery poke here says, if I remove the member, so rembero just means remove member, so remove the member matching H from the first list from the second list, and return that as the tail. So RV2 is the second vector with the element matching the head of the first vector removed. Yeah? And then recur with the tail of the first list and that remaining list. Keep spinning around like this until you have empty lists and succeed. And if you squinted it long enough, you can be convinced that that's a permutation. Yeah. Okay, so that's sort of an interesting thing. But now let's say, okay, let's talk more DSL. Let's say can lecture. So who can lecture dialectics? Only Aristotle. Now I was trying to avoid this, but it looks like this, right? All my remaining relations have this particular form where you can see my answer is passed in at the end. So I'm asserting some relation between some atoms and my answer. So I'm just basically pattern matching on all of this stuff. Let me get some answers up for you, and then we can explore them. We can explore them some. How much time do I have, Marco? 15, okay, cool. Okay, so I've said who can lecture various courses. Dialectics is Aristotle, mathematics can be lectured by either Archimedes or Aristotle, within my timetable. This is the key element. I'm passing my data around, there's no globals, often you can use facts in a relational program, I don't like it, I don't know what they are about, so I always pass my data around into my relations. So let's see if it gives me an answer for this. And it says, okay, sure, I've got some lecturers, now bind up. So rhetoric is lectured by Herodotus of Larissa. Rhetoric can be lectured by Herodotus of Larissa. It matches that pattern. It's found that for me. I didn't tell it how to find it. It just did. It ran through all the possible permutations and said, yeah, that's the answer. I can say, let's have a look at the can lecture quickly. It's a nice function. Okay, here it is. And it's the same kind of story. Now you can see how terse this all is. So this succeeds. So I have a query course and a query lecturer, which is a vector of lecturers who can give that course, and a timetable, right? And it's the same story. You've got a base case, and you've got two recursive cases. And you've got some destructuring and pattern matching happening in the arguments. So this succeeds. So what it's got the timetable here, and it's pulling off the first period, right? Same here, and then it recurs. So we've got some general thing that's going through the timetable, period by period, and matching stuff up against it. How does it match? This is quite cute. So it says, okay, if the course in the current period matches the query course, then bind me L1. So the course matches the query period, and I say, okay, well, the lecturer giving that course, L1, must be in my list of approved lecturers. If that's the case, happy days, and recur with the tail. So here's with the same query course and lecture, and the tail of the timetable. So I've matched that particular period, pull it off, recur with the rest of it, spin round. The other case is if the course in the period in question isn't the query course. So we're saying, who can lecture mathematics and the particular period in question is rhetoric. We don't care. So we just assert that the course isn't the query course and you recur. And That's the general pattern that I tend to use in all these things. So let's put in some more. Let's have some attendees, right? So who attends dialectics? The incanters do. In the timetable, see how this sort of thing gets threaded through everywhere. This is what I'm matching it against. The data is the core of what I'm talking about, right? So this is the same story. So I've got who can lecture stuff, who's attending what stuff. Let's look at some answers, right? We've got Herodotes, again, and now we've got some students sitting in there, right? So we're slowly building up our answers. It's quite interactive, and you can really play some fun games. But now let's throw a spike in. So, you know, Herodotes refuses to lecture rhetoric anymore. And now I have a problem, right? So now I've got, you know, rhetoric being lectured. So the first two periods, remember, are concurrent. And my lecturer here is Aristotle in both cases. So now I've got a problem. That pattern doesn't match. I can't have the guy in two places at once. So I can say, okay, also assert no concurrent lecturer. I think I've made a big mess here. But if I... Right? So you see, Herodotes is lecturing the first one, and Aristotle is lecturing the second one, but I've managed to mess up my demonstration. If I take this out, and I don't make that assertion, you see I've got Aristotle in both cases, right? So sorry about that, I was a bit mixed up. If I don't have, so if I comment out the assertion that there's no concurrent lecturers, I get Aristotle lecturing concurrently, but I can make this assertion, and then it goes away. Right, it's just pattern matching, right? I'll go there, but I won't hurt you by actually going through it. But so the general pattern I want to say about this is that the data is central to all of this. The answer I care about is the timetable. So let's deal with the timetable. Core.logic gives you ways of expressing relationships or sort of invariance across all the answers you can consider. And that's why it's powerful. If you can represent your problem as data, and we've seen already in the, you know, today, that you can do that in many ways, like in music. You can represent music as data. You can then say, well, compose me a ballad, because there's certain, you know, patterns that must exist within that data representation that semantically to me mean ballad. So you can say, compose ballads for me. You can compose shopping carts, or you can assert things on shopping carts. You know, this guy's not allowed to buy Earl Grey tea because he's intolerant to caffeine, whatever. Right? So you can use it in both those senses. And the most exciting one, sort of, as programmers, is sort of this idea of code as data is data. You know, a couple of tools coming out, like Ambrose with the type checker. Code is data, well, code as data is data. He's using it as data, asserting relations over it. You know, Kibit, which gives you hints about when you're doing non-idiomatic closure programming, that's the same thing. It's based on core.logic by treating it as a data structure. So I missed a slide. So why do you want to do that, right? The main thing is that you don't want to reinvent the wheel every time. You want to separate the search algorithm, how you find the answer, from what the answer is. So you'll note that in my talk, I just described the answer. I said, this is what a timetable looks like. It's got these lecturers. You know, these people are taking these courses. You know, this guy can't be in two places at once. He might be Aristotle, but he's not that good. You know, so you just describe the answer, and you don't care about how it's found. It has to go ahead and do that. So you're thinking about the answer, not how to get it. So that's sort of quite a powerful decomplectification, if you will. Like, I look at my code often, I say, my God, you know, I've heard, Rich, this is complected as hell. What do I have to do? I have to decomplectify. And, like, you can't get out of that. I mean, the word itself is its own betrayer. It's the complectification of a verb, a noun, and a logical negation. I mean, there's no way forward, right? Okay. So I'm done. In summary, you know, there are these old techniques that exist that have fallen out of disuse because they weren't pragmatic at the time. Lisp is one of them. Logic programming is another one. And what's inspiring and uplifting about closure is that these things are available and made relevant for us by being on the JVM. So we can plug them into the real world and use them. And I think the potential of that is just gigantic. So to move further, the guys who played the inverse all programmed to evaluate to 6 saxophone were Friedman and Bird. They gave a talk. It's the first, no, it's the second link here. You can't see it, but I'll put the slides up. Definitely watch that. It's just the most mind-blowing experience. Then Ambrose gave a talk also at the Conge last year, more about under the hood. So it's like, how does it actually perform this dark arts to which I've only alluded? Then go have a look at core.logic. It's the source code. It's well commented. There's a lot of links to other literature that's available. And then I've written myself a small tutorial just in the basics to sort of get you up and running with the stuff. So finally, thank you. Richiki, closure's been sort of like a Krakatoa of creative destruction in my life, and thank you very much for that. I appreciate it. Jim Dewey, he wrote the first logic, well, Canron implementation, and sort of taught me logic programming. I appreciate that. Dave for writing core.logic, and Christoph Grand for tolerating countless witless questions and answering them patiently. And finally, geeks ancient and modern who make this lark so much fun. Okay, I'll accept any questions stated in the form of goals. Five minutes.
Questions?
Nothing hard, please. Yeah. No, I've sort of, oh, sorry. Am I familiar with a Mozart programming language? No, I'm not. Right. Right, that's fantastic. Probably it could. I mean, why not? I mean, I don't know how to do it myself, but probably, yeah. It's certainly worth, I think that's a pull request right there, yeah? In ranking, yes, there is. That's a difficult question, actually. So there's an upgrade to, so the underlying technology is called Canron, and there's an update to that called C-Canron, which is Canron over finite domains. So you can then specify ranking and comparisons. In fact, let me show you. So something like that, yeah? So you can say that Q is a member of the vector 0.1, 0.2, or say 0.3. So these are ranked entities as numbers. And you can say, give me all the Qs that are greater than 0.15. Yeah, and it gives you 0.2, 0.3. So it can do ranking, yeah. This is not relational. This is sort of a hack on the system, but it's in the works to actually make a full relational thing, yeah. Yes? Yeah. I don't know. Under the hood, I'm not going to talk about it. I'll say wrong things.
Is there a way to actually, like, not only rank the answers, but like have relations, define relations on the answers to, for example, extract a minimal answer regarding a post function or like that? Like,
yeah, so say smallest of. Yeah?
Yeah, for example, for a timetable, we can
yeah, you could construct one, yeah. You could construct one. I mean, if you've got ranking, you've got most of algebra, so you could construct one, yeah. Yeah, last one.
Do you have any kind of optimization based on the declaration of flow patterns? And in that case, would you have these declared independently from your predicate and see any benefit from actually using closure to dynamically decide which flow pattern optimization should be?
Sure. Okay, so the question is, can we use Clojure to dynamically modify the engine under the hood that performs the answer? Is that what you're saying, based on the queries that are brought in? Again, that's way too deep for me. I just use this stuff. I don't know how it works. So, ask Dave. No, that's cool. Okay, before anybody else discovers I don't know anything, I'm out of here.